Hello, AP Stats. I hope you guys are having an awesome day. Today we're going to go on to 7.2, which is all about sampling proportions. So we briefly talked about sampling distributions in general, and now we're going to specifically go to sampling distributions when we're looking at proportions, meaning qualitative data, categorical data, because colors, for example, you can't find the mean of, so you want to find the proportion of a certain color. So what we're going to be doing is finding the mean and standard deviation of the sampling distribution of sample proportions, like I was just saying, for a simple random sample of size n from a population with a certain proportion p of successes. And just as a reminder, p can also be seen as pi as well. So we will also be able to look at whether the 10% in normal conditions are met in a certain setting, use the normal approximation to calculate probabilities involving p hat. Okay, so when can we use a normal distribution? Okay, and then we're going to use the sampling distribution of p hat to evaluate a claim. So basically we're going to do an example. Okay, so first we're going to actually look at how well p hat, so that would be your sample proportion, how well your sample proportion estimates the true proportion, p or pi. Okay, and so in order to do that, we're going to look at a little applet, and bear with me because I've never actually done this before on a video, so yay technology, we're going to try. Basically this is like a little Reese's Pieces candy machine, and we can set the probability of the true proportion of orange, okay, so pi or p, to be whatever we want it to be. So in this case, we'll go with 0.5. So we expect half of the, approximately half of the oranges in a sample to be 0.5 because the true proportion is 0.5. And so we're going to take a sample of 25 candies, and we're going to take one sample. And so here's kind of how that looks. And basically down here, you'll see the number of oranges pop up. Okay, so they're going to make a dot plot that just keeps track of how many oranges come. So we're going to draw a sample. Ooh, look! Okay, so out of a sample of 25, we got 13 oranges. Okay, so we're going to do that again. Okay, 17 out of 25 to be orange, which is, a large proportion, but, it's a sample, and so there's variation. So we're going to do this several times. I'm actually going to just throw a 10 in here and not animate anymore because that would take forever. So I'm going to draw, so that's 10 more samples. So that was 12 samples, and every single one of those dots, right, is the proportion of orange that was in that particular sample. So maybe I'll do it again, and do it again, and do it again, and 10 more samples, and 10 more samples. Okay, and what are you starting to notice? What is this graph starting to look like? Well, the more samples you take, right, the closer this is starting to get to, a symmetric distribution and approximately normal. And so, we expect about 12.5 oranges in the long run. So that's right about here. And so you kind of see that the distribution peaks at that. So we're going to go back and look at some of the questions and see if we can answer those yet. I actually have no idea how to make this bigger, but it just kind of does it on its own. That's fun. Okay. Sorry, people. Here we go. I'm trying. Okay. So the first question asks, how does the sampling distribution of the sample proportion p hat change with the sample size? Okay, we haven't actually looked at the difference in sample sizes yet, so let's do that. I'm going to drag that down for a second. And now let's look at if my sample size is a little bit smaller. So say I take out 6 candies. So we'd expect 3 oranges every time. So let's start over and draw 10 samples, 10 samples. Okay, we expect 3, but it's, you know, it's kind of looking, it's looking a little normalish. Most of our values are around 3 and 4, which is to be expected. We would expect more 3s. Okay, so, you know, it's not too bad. Let's see if we tried a sample size of 100. So this time, I am taking a sample of 100 candies. Okay, that's going to take forever. Lots and lots and lots of candies. And I'm going to stop. Okay, so we had 47 out of 100, so close to 50. I'm going to stop the animate and we'll draw 10 samples. And so we continue to draw 10 samples of size 100. Okay, and we expect this to be around 50, right? To be centered around 50. And if you look, like that's where the majority of the samples are. And so the more samples I take of size 100, the nicer this looks, right? So, question is, what exactly is happening as the sample size increases? Okay, and that's something to kind of think about. But as your sample size increases, right, you're going to tend to get a little less variation. So your standard deviation is going to be decreasing. And you can kind of see that in those examples that I just showed you. And likely more accurate as well, right? Because with larger samples, your proportion is going to be closer to the true proportion. Now, this is something else we haven't looked at yet. What about the difference between what the distribution looks like when p is close to 0 or 1 instead of 0.5? So now if we go back, and instead of having the true proportion of 0.5, let's make the true proportion of oranges 0.1, for example. And let's do a really large sample just so we can see this quickly. And we want 10 samples. Okay, we expect 10, right? Because we have 100 candies, 10% of them are orange. And so we're going to look at that distribution. Okay. Let's do this quickly. So let's go 100 samples. It looks like that, right? Here's your normal approximation. Okay. Now let's do that again with 0.5. So again, the true proportion of oranges is 0.5. I've got a sample size of 100, and I'm taking 100 samples. So let's draw that. Interesting. And that blue thing in the back, that's your normal curve. Okay, laid on top of it. Okay. So what you kind of see, maybe if we do 0.9 instead, and let's do a sample of size 1,000 or something, you're going to see that the data is a little bit more skewed than normal distribution. Okay, and so that's what's going to happen if your true proportion is close to 0 or 1, you're going to get slightly skewed data. And if your true proportion is around 0.5, it's going to get much closer to a normal distribution. Okay, so those are things to keep in mind as we look at the rest of this section. Okay, so that was number 2, and then the next question is, what is mu sub p hat, which is what is the mean of the sampling distributions? And if you take a look at these, generally they're over your expected value. So generally, when you're looking at these proportions in the sampling distribution, and basically what you're doing is you're creating a distribution of all the p-hats that you've gotten in all of your samples. So, p-hat looks like here, it's somewhere around 0.5 or 50%, which, you'd kind of expect because the true proportion is 0.5. Same thing if we draw, samples where the probability of the orange is 0.1, we expect about 10, and so it's pretty close to 10. A little skewed, but that's okay. Once we have enough samples, it's close enough to normal that we can start to do some calculations with it. So we're going to actually go into this mu sub p hat and then your sigma. Okay, so basically what you want to look at is that as long as your 10% condition is met, okay, so basically that your sample size is less than or equal to, no more than 1/10 of the population, then you have these two conditions. Okay, so I'm going to write that down for you. So as long as the 10% condition is met, again, I apologize for the writing. Namely, your sample size is less than or equal to 1/10 of the population size. Okay, you have a mean of the sampling distribution, mu sub p hat is how we denote that, and that's going to be equal to the true proportion of the population, which is pretty cool. So that means it's an unbiased estimator, which is something we talked about last lesson. Woo woo. And then your standard deviation of the sampling distribution of proportions is the square root of p times 1 minus p all over n. And there's a proof of this. If you're interested in seeing it, you can ask me in class tomorrow, or you can take a look at it in the book. But basically, it goes back to the binomial distribution that we learned about in chapter 6, I believe. Okay, so those are two conditions. So now we're going to start talking a little bit more about using the 4-step process, because you're really going to have to start checking these conditions. Anytime you want to use mu sub p hat equals p, you have to check that 10% condition. And then if you want to do any normal calculations at all whatsoever, okay, you're going to have to check to make sure that your sample size times your probability of success and your sample size times your probability of failure are greater than or equal to 10. Okay, so that's something that we also talked about before when we were approximating the binomial distribution with the normal distribution, and so that's why we need to use this. So again, if you want to use normal calculations, you have to check these conditions. Generally, they pass, right, because we can't really do much without it, but you always have to check them. All right, so we're going to try a few examples, and then that should be it. Okay, so let's look at this one. It says about 75% of young adult internet users, ages 18 to 29, watch online videos. Suppose the sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch the online video. What's the mean of the sampling distribution p hat? Then explain. Okay. Now, we can't really, the sampling distribution, remember our conditions from before, okay, as long as the 10% condition is met. So as long as our sample size is no larger than 1/10 of the population, then we're good to go. And so to answer question 1, we need to check, is 1,000 less than or equal to 10% of the population of, well, young people 18 to 29. Okay, so there's a lot of people 18 to 29, and so yes, 1,000 is not really going to do much damage at all. So we're going to check that off. Yes, that's true. And so the mean of the sampling distribution of p hat, mu sub p hat, is just going to be equal to the true proportion of the population, right? The true parameter, p, which in this case is 75%. Okay, next, you want to find the standard deviation and check that the 10% condition is met. Okay, we did that already, so you don't need to worry about that. So your sigma of your sampling distribution is the square root of p times 1 minus p all over n, okay, where p is your true proportion of success, so 75%. Times the probability of a failure, 1 minus p, so 0.75 times 0.25 all over my sample size, so divided by 1,000. Okay, so then you can calculate that with your calculator or whatever you have at your disposal. And you get 0.75 times 0.25 divided by 1,000, and then you take the square root of that. And you get something like 0.01369. Okay, so that's your approximate standard deviation of the sampling distribution. Okay. Now we got to figure out if the sampling distribution is approximately normal. Now again, remember our normal condition is this: np greater than 10 and n times 1 minus p is greater than or equal to 10. So for 3, we need to check for normality. So we do n times p, so 1,000 times 0.75, right? So 750. Is that greater than or equal to 10? Yes. Okay, and then we have to do it for a failure as well. 1,000 times 0.25, and that is 250, also greater than 10. We're happy. So we can use a normal distribution to approximate anything that we want to do, any of the data that we want to collect. Okay, so that is checked off. And then the last question says, okay, if the sample size were 9,000 rather than 1,000, how does this change the sampling distribution of p hat? Okay, so it used to be approximately normal. It has a mean of 0.75. It's got a standard deviation of 0.0 137. Okay. If we change the sample size, right, it doesn't change our mean at all, right? That has nothing to do with n. But it does, in fact, change the standard deviation. So the only thing that really changes is that your denominator, instead of being 1,000, is now 9,000. A larger denominator means smaller fraction. So your standard deviation is smaller, which means you've got, a more accurate, less variability on your normal distribution there. Okay, cool. So voila, that would be your answer to number 4. All right, last but not least, we've got one more example, and here we go. We've got a polling organization, and they ask a simple random sample of 1,500 first-year college students how far away their home is. Suppose 35% of all first-year students actually attend college within 50 miles of home. Keep in mind, eventually we're not actually going to know this amount. We're not going to know that proportion. But for now, we do, just so that we can kind of see how this whole deal works. Okay, so what's the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value? Okay, so basically, one, we want to check all of our conditions and check if it's normal. And then we want to find the mean and standard deviation of our sampling distribution. And then see if we can figure out this proportion. So first we want to check our first condition, 10%. Okay, is our sample less than or equal to 10% of the population? Okay, so is 1,500 less than or equal to all first-year college students? Okay, so all first-year college students, yes, that is definitely going to be correct. And then we want to check, our next condition was for normality, because if we can approximate with a normal distribution, we would love to do it. So let's check NP and N times 1 minus P. So N times P is 0.35 is our probability of success times N. Sorry, I did that out of order there. Times 1,500. And we want to know, is that greater than or equal to 10? Yes, definitely it is. N times 1 minus P, which is 1,500 times the opposite of 0.35, the complement, right? So that's 0.65. Is that greater than or equal to 10? Yes. Okay, so all of our conditions are met, which means we can now find the mean, standard deviation of the sampling distribution, and use the normal distribution to approximate them. Okay, so conditions are met. Yay, we're happy. That doesn't do the circly thing. Okay. So let's create our sampling distribution. So it's going to be normal, approximately normal. Okay, with a mean of the true proportion, so 0.35. And then our standard deviation is the square root of P times 1 minus P all over N. Okay, where P, 1 minus P, 0.65, sorry, let's do it in the right order. 0.35 is the probability of a student being 50 miles away from home or less, and then 0.65 all over 1,500. Okay, so I can get my calculate my standard deviation, so 0.35 times 0.65 divided by 1,500, and then we want to take the square root of that, and we get our standard deviation to be approximately 0.01 0.23. Okay, so I'm just going to clean this up a little bit. Okay, and now I can use either the normal CDF on my calculator, or I can use my z-score, right? But the question was, what's the probability that a random sample will give a result within 2 percentage points of the true value? Okay, so we want, we would be happy from if our sample had anywhere between 33%, oops, and 37% is where we would, where we're interested in. Okay, so we can use normal CDF, or we can use the z-score table and find the probability that the values of my proportion of samples would lie between those two values. So bars, right, my distribution, and I want my normal CDF, and I want to go between 0.33 and 0.37 with a mean of 0.35 and a standard deviation of 0.0123. And then I enter that and see what that probability is, and I get 0.89605, 0.8961. So we want the probability that my sample proportion is between 0.33 and 0.37 is approximately 0.8961. Okay, and then that would be my answer. Okay, so that's kind of your two types of examples that you'll see. So hopefully that made sense, and I hope you have a wonderful rest of your day. Woo woo! Okay.